for coming to Lecture 7 of Intro to Space Navigation, Spring 2025. So this is going to be hopefully a shorter lecture, and also I recognize that we're kind of outside of the normal class time right now. Going to be traveling tomorrow, so we need to do lecture during office hours. So thanks for putting up with that. I'm going to try to make it up to you by making this one shorter. And today is going to be the first of a two-part series on initial orbit determination. Let me write that down. Initial orbit determination, or IOD, and this is part 1. Yep. All right. So the idea behind initial orbit determination. So we've talked about how to go from the position and velocity of some body to orbit elements. We've talked about the physics that is underlying the problem at play. So either using Kepler's equations to model things, or using the two-body equations of motion. The next idea that I want to talk about is reconstructing a full state from several partial states. So remember that navigation, all the way back in our first lecture, navigation equals, actually, you know what, that might have been in the PowerPoint. Navigation is estimating state, which we usually think of as position, velocity, and attitude, from available measurements. So you can think of measurements as information about your state. So today's problem is estimating orbit elements. So that's orbit determination from available measurements. But remember that orbit elements is position and velocity. So it's really estimating full state from several partial states. So in practice, orbit determination takes the form of velocity finding. So most of the time, what we have is either multiple positions or multiple measurements of your position. And what you're looking for is the velocity corresponding to any one of those positions. That's the idea. Or you have a whole bunch of measurements and you're trying to reconstruct position and velocity. But the big thing is we generally measure position or range or angles, which are all position things. We don't as much measure speed or rate of change, range rate, that sort of thing. Although we do sometimes. Most of the time, for the classic orbit determination problems, it's velocity estimation, because if you know your position and you can surmise your velocity, now you're back to your full state, and your full state is your orbit elements. It's the same information expressed two different ways. So that's the idea behind orbit determination. So using measurements, it's time for a formal definition. Using measurements of the motion of a body to estimate its orbit typically under the assumption of two-body orbital dynamics. Is initial Orbit determination. Or IOD. There's a separate problem. So by contrast, determining path a body will follow with a high degree of accuracy. That's like accounting for perturbing effects. Is precise orbit determination, which is outside the scope of this class. All right. Promise we're almost done with the writing. It's about to be a lot of math, so enjoy the writing while we can. When performing IOD, the objective is usually to find position and velocity at the same time. We'll say the same instant in time. I don't mean that you need to solve the equations at the same time. I mean like at some instant t that we're finding the position and the velocity of the spacecraft. Because at that point, this is equivalent to knowing the 6 orbit elements, right? All right. So in this and the next lecture, we will cover 3 classical IOD approaches. Yes. And 2 modern ones. So you could think, what partial information would you need to reconstruct an orbit? Well, one of the simplest ones you could think of as if you have a whole bunch of position measurements, in theory, enough positions, and it's 2-body orbital motion, you could fit an ellipse to all of those positions, and that would give you your orbit, and ultimately you could determine your velocity. That is the first one. So today, it's going to be 3 positions, which is Gibbs method. Sorry, S apostrophe, because his last name is Gibbs, not Gibb. You could also have 2 positions and some delta t, the time between them. This is referred to as Lambert's problem. Or you could have 3 or more line of sight measurements, which is typically Gauss's method. That's the classical. But also more recently, Gooding's method. So 2 different ways of handling these measurements. And then also much more recently, like I said, typically we're doing estimating velocity from position or information about position. So line of sight measurements to an object is kind of 1 or 2 degrees of freedom of its position. But you could also attack the problem from a completely different direction and say, what if we knew its velocities over time, but we didn't know its position? And so one of these would be 3 velocities, ultimately trying to determine its position. And so, for lack of a better term, I'm going to call this the Christian-Hollenberg algorithm. And there's also the 2 velocities and a time of flight. We're going to leave that out for this class. There's going to be other I like to mention the 3 velocities one because that was developed right here at RPI in the last decade. So this is like state-of-the-art stuff. So, all right. First is going to be, we're going to do 2 of these today, then we're going to call it. Then we're going to do 2 of them, or sorry, 3 of them tomorrow. Are we going to have time for that? Let's see. Today is going to be 2, 3. I think we should be good. We're just going to do the 2 today, keep it nice and short, and then we'll do 3 next time. Because we're going to have a relatively light covering of Gooding's method. So I think the dense ones are going to be Gibbs, Lambert, Gauss, and then the Christian-Hollenberg method. So let's talk about Gibbs. Any questions up to this point? We good so far? All right, so far so good. So the man of the hour is Josiah Willard Gibbs, who lived from 1839 to 1903. He studied at Yale. He was the first American to get a PhD in engineering. And he is also the father of modern vector notation. So the fact that, we have matrices and we have column vectors and you do multiply the rows of the first columns of the second, that was this guy, father of modern vector notation. So you might expect that his method is going to be lots of vector math, and that is where we're going. So let me draw a picture here. So imagine that you've got some position, R1, and then some other position, R2, and then some third position, R3. There is only one ellipse which fits, oh, well, maybe if I could draw this line a little bit better. There's only one ellipse which fits all of those and orbits the central massive body. That's essentially the idea behind Gibbs' method. So Gibbs' method IOD, find a conic section that connects 3 position vectors. Or in plain English, given R1, R2, R3, find, usually we'll do V2, but we'll just say VI for now, any one of those. If you have R1, V1, you're done. If you have R2, V2, you're still done. If you have R3, V3, you're still done, right? Any of those would be enough information to get the whole orbit. So you see how we've gone from something really nebulous, like what is the orbit of a body in space, to something much more concrete, like 3 position vectors, using the assumptions of 2-body orbital motion, using maybe some of the equations that we've learned in orbital mechanics, find some way to kludge together a solution for velocity. That is a much more solvable problem than just find the orbit of this thing. And so I want to go back. First of all, I'm going to rewrite the word method because I think I could do better. That is exactly the sort of thing that it's kind of the goal to learn as you're a graduate student, is not just how to solve the problems that are handed to you, but how to carve off a solvable problem from the kind of infinite abyss of unknown things. So I want to just kind of marvel at the elegance of just the Gibbs method setup before we go into 3 pages of math trying to solve it. So one of the things we want to observe before we go any further is, why is 3 positions enough, right? In general, if I'm not mistaken, and I hope I don't say something stupid here, I'm pretty sure it's 5 points in space is enough to fit a 2D ellipse in 3D space, but we only need 2. And the difference is that even though we have, in general, you would have this kind of unknown about the position of your body, or position of your orbit, we can leverage the fact that one of the foci of the orbit ellipse is the center of the central massive body. So in the frame that we're working here, it is the origin. So you only need 3 positions to determine a ellipse which is centered at the origin, or has one of the foci at the origin. All right, it's math time. We begin with the equation for eccentricity. So remember, E is equal to velocity cross specific angular momentum divided by mu minus normalized r, right? Or r, the direction. Okay. If you rework things a little bit, you get velocity crossed with h is equal to mu r over r minus e. Or I'm sorry, plus. First mistake. There we go. Okay, that's just a little bit of algebra. So after some vector manipulations, we're going to skip a few steps. This becomes that velocity is equal to mu over the scalar h squared, and then in parentheses, h crossed r divided by r plus h cross e. So we're skipping several steps to get to this point. Okay. Now we're also going to say, recall that your eccentricity is just the eccentricity scalar, and it's in the parafocal frame p direction. Remember, we defined p as the direction pointing along eccentricity. And then similarly, we can say that specific angular momentum is the specific angular momentum scalar multiplied by the w direction. This is just by definition, right? So that allows us to say that velocity is mu over h, and then in parentheses, w hat crossed with r divided by r plus, this simplifies to just e q. Okay, so let's pause for a minute. We've done some math. Why do we care about this equation? This means if we know specific angular momentum, the w direction, and the q direction, we can solve for velocity as a function of position. Okay. So here we have the 2-body orbital motion kind of implicitly already in our equation here. So this equation is going to be our home base. This is going to be kind of the campfire that we return to as we go off and do some kind of fancy math. So what we'd like to do then is find expressions for h, and then for w, and then for q, and try to put things together. Okay. So, on. Here is a crucial observation. which makes a solution to Gibbs method possible. All vectors, or all position vectors, are coplanar. So therefore, any one is a linear combination of the other two. Okay, so what does that mean in terms of math? Well, it means that R2 is going to be some C1R1 plus C2R2. So some scale, and you kind of see this in the diagram here. Imagine R1 and R3 form a set of basis vectors. Some scaled R1 plus some scaled R3, even if, or sorry, ooh, somebody should have caught me. This is a 3. Sorry, I'm tired. Here we go. Right. Some scaled R1 and then some scaled R3 added together get you back to R2. Now, what are these constants? We don't know yet. So these are unknown. Solve for later. Okay. Now, what we can also do is we can say R2 dotted with E, the eccentricity vector, is C1 R1 dot E plus C3 R3 dot E. Okay. However, we can make a substitution. And that is that R dot E is equal to H squared over mu minus R. So this gives us H squared over mu minus R2. Do I have my notes backwards here? Yes, I do. Sorry about that. I have a typo in my handwritten notes. I'm trying to kind of troubleshoot in real time here. This should be C1 H squared over mu minus R1 plus C3 H squared over mu minus R2. Okay. Let me just correct my handwritten typo here. This should be a 2. This should be a 1. There we go.
Should it be 2, 1, and 3 for the R's?
There I go again. Thank you. While I was staring at a typo, I made another typo. There we go. Perfect. This is why the lecture needs to be an interactive session. Okay, cool. So let's keep moving then. All right. And this is where I'm going to skip some steps. There's much more intricate derivations that don't spare any gory details, which you're welcome to go read. But we're going to skip a bunch of steps, try to get to the answer in a reasonable amount of time. So after quite a bit of manipulation, what we get is something that looks relatively simple. We get this vector capital N is H squared over mu times this vector capital D, where the vector capital N is some combination of vectors. So this is where Gibbs, being the hero of vectors, kind of shines through here. This is going to be the scalar R1 times the vector R2 crossed with the vector R3, plus the scalar R2 times the vector R3 crossed with the vector R1, plus some scalar R3 times the vector R1 crossed with the vector R2. And D is R1 cross R2 plus R2 crossed R3 plus R3 crossed R1. Okay, how does this help us? Well, one can compute hopefully it's straightforward. You can get N and D from 3 position vectors. So those are functions of things that are given. And then solve for H. Okay. So in this case, we would say H is equal to the square root of mu N over D, where N without the vector bar is just normalized vector N, and then D without the vector bar is normalized vector D. Okay, so remember, we're going to look up here. If we know H, W, and Q, then we're done. We've just demonstrated that we can figure out H. Okay. Now also, scroll down a little bit here. Looking more closely at D, let's look at D. It's R1 crossed R2. But whatever that is, I have no idea what the magnitude is going to be. But if you just look at the vectors here, it's going to be something that is up in the K direction, right? And then 2 crossed 3 is also going to be in the K direction, or kind of the Z direction. And then 3 crossed with 1 is going to be also in the K direction. So you're going to get something that is going to be entirely perpendicular to, I guess it could be negative, but it's definitely going to be all out of the plane. So the plane, pardon me, formed by R1, R2, and R3, after you do all this cross product business, is going to be, or this D is going to be entirely out of that plane. So looking more closely at D, it must lie along the W direction. Therefore, we can say W is just the direction of D. Now, you might still run into an issue. Is it possible that W will be the wrong way? It's like, yes. That's where you would need to go sure that R1 crossed, I guess it would need to be, yeah. 1 crossed 3 should give you roughly the W direction. That's kind of the idea here. So we can get W from D over D. I saw a raised hand, Michael.
Yeah, does it matter which order the 1, 2, and 3 are with the positive and negative? Like if you cross 3 with 1, it should give like the negative W hat, right?
3 with 1 cross, yeah, 3 cross 1 is negative 1 cross 3, right? So like in that case, order matters. Does that answer your question, or am I missing you?
I'm more asking, like, is there a convention, like, do you go like clockwise 1, 2, 3, counterclockwise, or doesn't matter?
Like the order of these 3, or like
order of these 3.
Oh, I mean, I guess you could just as easily like switch the order this way. Or do you mean the order like it needs to be 1 cross 2, it can't be 2 cross 1?
I guess it's both because they're tied with each other. Because like in the you have 1, 2, 3 going counterclockwise. Does that matter, or can like 1, 2, 3 go clockwise and you get the same result?
I'd have to think about that for a little bit. So I suppose, so I mean, you have to follow the right-hand rule, right? It needs to be that 1 cross 2 equals 3. That's kind of a given for a right-handed system. Could you play around with the order of these things and it would all wash out? Maybe. I don't know enough to say that that wouldn't work. But I do know enough to say that as written, this will get you the answer.
Okay.
That's a good question. I'm going to have to plead ignorance on that. I think maybe, Sam.
Okay, sounds good.
Okay, so let's move back then. So remember, if we know H and we know W and we know Q, then our home base equation is done. Next, we need Q. But actually, we don't really need Q. We need E times Q. So we might be able to play some trick and essentially solve for EQ. Okay. And next page of my notes. So first we'll say, recall that Q is W crossed with P. Okay, but now P is just the direction associated with the eccentricity vector, right? So we could just as easily say Q is W crossed with the eccentricity vector normalized, because that's what P is. So we're just making a direct substitution. Okay. But now W crossed with E over E. Okay, well, let's multiply both sides here. EQ is, in this case, EW crossed with E, which, if you do some more manipulation, and there's a lot of, I promise the cross product stuff works out. This works out to be D crossed with E over DE. Hopefully that makes some sense. D crossed with E over DE gives you EQ. Or sorry, whoops. I knew something looked fishy here. There's no E in the denominator. It's just D. So D crossed with E over D gives you EQ. All right. So now, finally, if you wanted to, we can skip a step here. Vector manipulation will show that S is D crossed with E, which you could just compute D crossed E. But this is also R2 minus R3 R1 vector plus R3 minus R1 R2 vector plus R1 minus R2 R3 vector. So this is done just to save us a little bit of time. Once again, we have some vector which is built out of some combination of R1, R2, and R3. Finally, we can say EQ is just S over D. All right, so we're done. So we have EQ, we have W, and we have H. So we can go back to our home base equation, some function of the positions that we have so far. So we're going to show some kind of few more steps, and then we're done. Hopefully it shows that we're coasting to victory at this point. So thus, our original equation for velocity becomes velocity is equal to mu over h. We're going to substitute. This is now d crossed with r over dr plus s over d, okay, which is also equal to mu over h d, d crossed with r over r plus s. All right, we can even take it a little bit further. So I'll say mu over hd is the same thing as mu over d square root of d over un, which is mu over square root mu dotted with square root d over d dotted with 1 over square root n, which works out to be the square root of mu over n d. So again, we're using a little trick here to not bother computing h. So if you wanted to, you could just go through and manually compute h. We're going to make this substitution here. H is square root mu d over n. And by the time we're done, we end up with this vector equation, which this is our final answer, by the way. Velocity is square root mu over n d, open parentheses, d crossed r over r plus s. And that's it. Final answer. So now, for any one of the positions, you can find the associated velocity. And all you need is n, d, and s. but S is just some clever combination of the position vectors. N is some clever combination of the position vectors, and D is some clever combination of the position vectors. So when you're coding this up, which this is part of homework 1, it is the simplest thing. I think it's like 10 lines in MATLAB or Python. So the Gibbs method procedure is step 1. Use R1, R2, R3 to compute N, D, and S. Space that out a little bit better. N, D, and S. Okay. And then number 2, calculate VI corresponding to any position. And then step 3, optional. So if desired, you could say RI, VI gives you your orbit element. So that would be not theta dot, that would be theta I, and then E, A, capital omega, inclination, and omega. That's it. So very straightforward to go through and code up. So on the homework assignment, you're asked to come up with basically 3 positions. So you could even just use Spice to find 3 positions of the satellite, and then you plug it into Gibbs method, and then you find the corresponding orbit elements. And that's it. So questions on Gibbs method? All right, cool stuff.
Does it matter how close? Does it matter how close the vectors are? Like, is there, or just anywhere?
What a good question. I love that. Okay, great. So mathematically speaking, right, if you have 3 points, you can fit an ellipse to them. But the thing is, this is not a math class, this is a navigation class, and real measurements have noise on. So a lot of the time when we're looking at our navigation methods, we have to think about how sensitive they will be to noise. So hopefully it makes some sense, and I guess I'll that question. Good job. Hopefully it makes some sense. We'll just do a 2D problem here. That if you've got, this position, and this position, you're kind of well suited to fit an ellipse to those 3 positions, right? But if you have, say, this position, and this position, and they're all a little bit noisy, like you're not really sure if you're right about those, that there would be a whole family of like reasonable solutions to that problem. And so you do need to worry about something called observability. So what we're going to do for this class, we're going to say, let's find 3 positions that are relatively well spaced out, all within the span of a single orbit. But if you are forced to use 3 position measurements that are close to one another, there's actually a different algorithm called Herrick-Gibbs, which is better suited for that problem, which is kind of more robust to sampling less of the position of the orbit ellipse. Yeah, good question. All right, other Gibbs method questions?
Would you be able to just repeat what you said for step 2? I just can't read it very well on my screen.
Oh, sorry. Step 2 is calculate the velocity corresponding to any position vector.
Okay, thanks.
Yeah, I'll try out. I think my handwriting is getting a little better, but we're still not there yet. Calculate VI corresponding to any RI. There you go. Okay, neat. So we're going to take a break for about 10 minutes, and then we're going to go over Lambert's problem, and then we'll be done. So hopefully a little bit shorter. So it's 6:48 for you. Let's take a break and say back at, and let's just say top of the hour, back at 7 o'clock. Welcome back, everybody. So we're going to do one more orbit determination method, and then we're going to stop for the day. The next one is Lambert's problem. So unfortunately, is to get through these orbit determination methods to skip some steps in the derivation, but ultimately show that, okay, 3 positions, you follow this algorithm, you get the thing. Lambert's problem, you follow this algorithm, you get the thing. I tried to kind of split the difference between, I could just tell you, here's the solution without the derivation, or we could spend a whole lecture going into gory detail on all of it. And I tried to kind of go middle of the road, which you might find unsatisfying because there's going to be some steps where I go, and then, after skipping all this, we arrive at this next step. So if you want to go into full gory detail, we can talk about it, or I can point you to some references, but I'm going to give you kind of a Cliff Notes version of this derivation. The problem with Lambert's problem and the derivation of the solution of Lambert's problem is that it gets pretty gory, and some of the skipped steps are going to feel like I skipped a million miles. So try to bear with me. We'll see how far we can get through this here. So Johann Heinrich Lambert posed the problem of finding an orbit given 2 position vectors of an orbiting body and a time of flight between them, like a delta t. So it's called Lambert's problem, but it was solved not by Lambert, by Joseph Louis Lagrange. Yes, that Lagrange. Using Lagrange coefficients. So the problem setup is, if you've got some orbiting body, so here's the central massive body. Let's say that you've got some position 1 here, which we'll call R1. And let's say that you've got some position 2 out here, R2. And you're looking for an orbit that connects these two, but you also have some delta t between them. This is also a solvable problem, so only having 2 positions at the time of flight. Now, the solution to this problem may be in your imagination. We're talking about time all of a sudden, so it's not just going to be vector stuff. It's probably going to involve either Kepler or some other system of describing future positions and velocities as functions of current position and velocities, and that is exactly where we're going. So the problem statement is given R1, R2, and delta t, find V2. We begin with what are called Lagrange's equations, which use Lagrange coefficients. So we begin Lagrange's equations. So R2 is some function of R1 and V1. So it's f, where f is a scalar, it's not a function. F scalar R1 plus G scalar V1. And then V2 is f dot R1 plus G dot V1. So the idea here is we're kind of going back to that discussion from earlier. If you've got a linear combination of the first position and the third position gives you the second position, that's kind of the idea. Well, here we're saying that some linear combination of the first position and the first velocity gives you the second position, because they're going to be in a plane together, and some linear combination of the first position and the first velocity gives you the second velocity, where these magical numbers f, g, f dot, and g dot, which it's really tempting to call them functions because like there's a dot here. These are scalars, are Lagrange coefficients. These are scalars. All right. So let's go through. We're all about the velocity because we know the positions. So you could say that, okay, V1 is 1 over G R2 minus FR1. And then V2, which is kind of the one that we're after right now, is 1 over G dot R2 minus R1. That sound right? Let's see. V2, if we are, oh, I see. Yep, sorry. That took me a second. I'm like looking at my own notes. We're substituting the velocity into the V2 equation. So we want V2 as a function of R1 and R2. That's the idea. So we plug V2 in here, or V1 in here. All right, sorry, a little bit rocky there. So now we introduce a new concept of, so we've heard about true anomaly, we've heard about eccentric anomaly, and we've heard about mean anomaly. Here's a new one, universal anomaly. We're going to use the Greek letter chi, which looks awful lot like an X. And the thing here is that this is valid for closed and open orbits, so elliptical and hyperbolic. So we're making no assumption about this thing being on an actual orbit. It could be on a flyby trajectory, right? So that forces us to use some method of describing the orbit, which does not have, like, theta, true anomaly, it's baked in that you assume that it is a closed orbit, that it's an ellipse or a circle. Right? If pi is 0 at some initial time, so t is t naught, then pi at some future time, so t naught plus delta t, is found, sounds like Kepler's equation, right? This is found by solving another thing which we're going to introduce, the universal Kepler equation. So I mention this now because we're not going to use it outside of this derivation, but you might remember from our Kepler discussion, there's a set of equations for a closed orbit, there's a set of equations for an open orbit. If you go nuts with the math, you can end up with a set of equations that work in either case. And that set of equations looks like this. So it's the square root of mu delta t is equal to r naught scalar, v naught scalar over square root mu pi squared c of z, we'll talk about what that is in a second, plus 1 minus 1 over semi-major axis r naught pi cubed s of z, talk about what that is in a second, plus r naught pi. So it's a weird equation, seems to be coming out of nowhere. Let's talk about this and let's talk about this. Otherwise, it's things that we recognize, right? R naught scalar, V naught scalar, semi-major axis, mu, R naught again. So, okay, seems reasonable. We just need to make sense of C of Z and S of Z. And also Z, kind of snuck that in there too, where Z is chi squared divided by semi-major axis. So it's just a scaled version of your, or kind of a modified version of your universal anomaly. And C of Z and S of Z are a class of functions called Stump functions. So named because I would have been stumped if I tried to figure this out. Okay. So without derivation, C of Z is the sum from k is equal to 0 to infinity of -1 to the power k, z to the power k over 2k plus 2 factorial. And then S of Z is sum from k equals 0. Oops, tie that up a little bit. The sum from k equals 0 to infinity of -1 to the power k, zk over 2k plus 3 factorial. So these kind of drop out of nowhere. Maybe to make them a little bit friendlier, I'll remind you that the exponential function, which is just e to the power of x, is the sum from k is equal to 0 to infinity of, what is it? X to the power k, k factorial. All right. So, you know, not, do I have that right? Yeah, I'm pretty sure I do. Point is, this is a class of function which, while it looks like it's kind of out of nowhere, I mean, it's not that different than the exponential function. Maybe we shouldn't be too shocked that we see Euler stuff popping up here or something that's kind of Euler adjacent. But anyway, here we have C of Z, S of Z. These are functions of Z, which you can compute. Z is some function of universal anomaly and semi-major axis. So hopefully we see that while this is weird and it drops out of nowhere, this is an equation that allows us to map universal anomaly from some present time onto some future time. Okay. Why do we bother with this? Well, because our kind of home base is these Lagrange equations. And you can actually work backwards and solve for the Lagrange equations or the Lagrange coefficients as functions of these kind of weird, you know, universal anomaly and Stump functions and so on. So after some manipulation, we can solve for the Lagrange coefficients. And it would look like this. F is 1 minus pi squared over R1 C of Z. G is delta T minus 1 over square root mu pi cubed S of Z. G dot is 1 minus chi squared over R2 C of Z. And we actually don't need F dot to complete this derivation. So we're going to skip that one. And we've also skipped a ton of steps to get to this point. So for now, we're going to take our word for it that if we can figure out this whole universal anomaly business and these Stump functions, now we have these Lagrange coefficients, which allow us to solve for V2. So remember, our goal is to solve this equation right here, too. So we need G, we need G dot. We'll also need F at some point. So we're going to use these Stump functions. Now let's make this make a little bit more sense. Some further analysis will show that pi is equal to the square root of y of z over C of z. So C of z is this Stumpf function. Y of z is some other function, and it is R1 plus R2 plus A z S of z minus 1 over square root C of z, where A is sine of delta theta. Okay, finally something familiar. Delta theta, the change in R, true anomaly, square root R1, R2 over 1 minus cosine delta theta. Yep. All right. We can also, if we assume an elliptical prograde orbit, that is to say that we're moving with the rotation of the Earth, not against the rotation of the Earth, then we can also say that R1 crossed with R2, all of this, the z component is going to be strictly positive. Then we can say that delta theta is the inverse cosine of R1 dotted with R2 divided by scalar R1, scalar R2. So you can compute delta theta as just the angle between the two position vectors where those two position vectors are scaled. Okay, great. All right. So we need z to continue. So we've done a lot of setting up. Then everything will fall like dominoes. You know what? I don't need to write that. That's fine. We can just say that verbally. So hopefully that makes some sense. Delta theta is some function of R1 and R2. Okay. If we know delta theta, we can find A. If we know A, we can find Y of Z. Well, not exactly. We still need Z. That's the big question that remains. Okay. What exactly is Z in this case? Well, Z is universal anomaly squared over A. Universal anomaly should be some function of theta, maybe. So we need some sort of relationship between theta and universal anomaly. Okay. And what we will do here is, let's see, we're going to end up solving for Z numerically. Okay, with some initial guess. So the iteration is going to go like this. Z at the next iteration is Z at the present iteration minus some function f of Z at the present iteration divided by some function f prime of Z at the present iteration, where f of Z is equal to y of Z over c of Z to the 3/2 power S of Z plus a square root y of Z minus square root of mu delta t. And then f prime of Z is even worse. It's y of Z over c of Z to the 3/2 power 1 over 2z c of Z minus 3/2 S of Z divided by C of Z plus 3 over 4 S of Z squared divided by C of Z plus A over 8, 3 S of Z over C of Z square root Y of Z plus A square root C of Z over Y of Z. Close, and then close again. All right. So this may feel like we're kind of at the bottom of some great chasm because we've been doing some weird alien math for a little while, but we're actually done. Okay. So what do we mean that we're done here? Well, if we know R1 and R2, we can solve for delta theta. If we know delta theta, we can solve for A. Okay? And then if we know A and R1 and R2, we can solve for Y of Z. But in order to solve for Y of Z, you need Z. So we kind of guess a number for Z. And then we solve for Y of Z. And then we solve for S of Z. And then we solve for C of Z. And ultimately, we crank out this capital F of Z and this capital F prime of Z. And then we actually compute a new Z based on our previous guess. And we do this until we converge on some Z. And then when we're finally done with Z, for one last time, we go back and we solve Y of Z. We solve for universal anomaly. Then we go through and we have our Lagrange coefficients, F, G, and G dot. If we have F, G, and G dot, we can solve kind of our home base equation, either V1 or V2. In this case, we're going to do V2. And if we know our velocity, so a whole bunch of really fancy, weird math that we're not used to, but this is all eminently solvable. And you can code this up lickety-split. It won't be too bad. So thus, our Lambert procedure is step 1. Using R1 and R2, find delta theta A. Step 2, assume that Z is some, we'll say Z naught, some small positive value. Then iterate until convergence. Using F of Z and F prime of Z. All right. When we're done, we found an actual value for Z for convergence. So then we say find Y of Z and then find chi, the universal anomaly. And then find Lagrange coefficients. The only ones we need are F, G, and G dot. And then we'll say find V1 and or V2. Typically, we'll do V2. And then, if desired, R, I, and VI can be used to find theta I, E, A, omega, I, omega. That's it. That is Lambert's problem. So we've demonstrated that with Gibbs, 3 positions gives us a velocity. And we've demonstrated that with Lambert, 2 positions and a time of flight gives us velocity. And that's pretty much all I got for you today. So unless anybody has any Lambert questions, we can break. If you have any homework questions, we'll talk about those too, but we'll do that after the recording stops. Going once, going twice. All right, I'll wrap up the recording. Thank you everybody for coming, and then I will go ahead and post this so that the folks who couldn't make it today can watch this as soon as possible. All right, thank you.